Well, that's true. It should have kind of been like I was here anyway. So quickly, just to reiterate, we are, we have hit the halfway point, which is, of course, a good time to be taking the midterm, to be at the midway point. Now, when we say midway point, it's halfway chronologically. We're probably over halfway, definitely over halfway when it comes to material, though, because the integral, the second half of the material, the integral, is, as you'll find out later this week, is connected to the work we've been doing already. So you're going to see and hopefully understand a lot of these connections to things we've done as we learn the derivative. The process can be very similar. We're going to start graphically, kind of like we did with derivatives, and then work more into the symbolic, but we'll do it a lot quicker. We'll make that jump a lot quicker into that. And our next quiz will be on Tuesday of next week. And the basic problem is, how do you remember we did this the first couple days? There's two main problems in basic calculus, and that is the tangent line problem, rate of change, instantaneous rate of change. How do you find the rate of change at one point? Kind of solve that problem with the derivative. And then the other problem was, how do we find areas under kind of odd-shaped regions? That's the problem we're attacking now. How do we find these areas? So first we got to get some notation, just like we started with instantaneous rate of change. We said, let's put this little prime thing on our f, call that f prime, that means derivative. Well, same thing here. We're going to have this integral. We're going to call this the definite integral. We're going to have this S kind of shaped curve is going to be our integral symbol. And this means the area between the function and the x-axis. And important to understand, we're talking about the signed area, right? Because area that's below the x-axis is what? Negative, right? Area that's below the x-axis is negative. Okay? All right, so homework. Homework. Is your homework real quick? I might come around the area. Okay? You weren't here the other day.
I went to a funeral
Yeah.
over the weekend, so I did not know.
Okay. Just a quick idea of how many questions we might have here. Okay, so a couple of things in that you should have got from the video. We always start with this number down here, and then we read to there. So when we read this, we say that's the integral from A to B. The integral of f of x dx from A to B. The dx part is just kind of notation. We're going to learn more later on about what that's about. Right now, it just means with respect to x. There are times that we will just call this the integral. There will be a lot of times in your book where they just do that. It's kind of like the difference between doing f prime and f prime of x, right? The f prime, we understand what we mean. We can use that, but the of x helps us know it's with respect to x. We found out later on that was pretty important to know what it's with respect to, okay? Well, there'll be times where that's important too, and we'll talk more about what that dx and where it comes from. But for right now, it's just notation. Excuse me, just notation. Kind of hangs out there. The key is, that this is the curve that you're doing. A lot of times we say the area under the curve. That's a term that's used a lot for integral, but we do have to be careful of that, because if my function was down here, I'm not sure that this feels like area under the curve. Almost feels like area above the curve, right? So, but we say area under the curve means between the curve and the x-axis. That's what we mean. Between the curve and the x-axis. Area down here is negative, area up here is positive. What happens if these go backwards? Then the area is opposite, right? So if you do the integral from B to A, this red area would be positive, and this blue area would be negative. It's opposite if those are written backwards. And then by backwards, I mean if you went from 4 to 2, right? That's backwards. okay, from 4 to 2. It should, normally it's going to be the integral from 2 to 4. Okay, so normally the smaller number is going to be down here. That's normal. Okay, when we write an integral, we want to always, if we have an option, we're always writing it this way. Now we'll see why there are times it sometimes is written backwards. So we just need to understand that that's opposite. Okay, so we had some stuff here. You had some rules where you can split apart. So this is kind of like your derivative rules as well. You know, if you got x squared plus 3x, you can do the derivative of x squared, do the derivative of 3x. Here you can do the integral of f plus the integral of g. If you have a constant out front, a derivative, it just hung out there. Same thing here. If you got a number multiplied by a function, you just pull it out in front and just hang out there while you do this area. Okay? All right. So we had an example of that. Okay, I'll come back to that here in a minute. All right, so on the homework, any of those you want to talk about or you have questions about? 38. Okay, anything before 38? Again, don't be afraid to ask because this is really foundational stuff and we want to make sure we feel really good about it. Okay? Now, I will say this. For us right now, if we're going to find this value, now, and keep that in mind, this is nothing but a number. Just like f prime of 2 is a number. It's a slope of the function at 2. A definite integral is just a number. It's an area between that function and the x-axis between point A and point B. It's a number. We have two ways of finding that number right now. Think back to slope. What were the ways we had of finding f prime of 2? Well, in the beginning, we just picked two really close points. Remember that? The best we could do was approximate. But now if it happened to be a line, then we could find the slope because we knew how to do slope of line. Well, that's where we're at right now. So one way to find this area is if it makes a geometric shape. So if we have a graph, either like this one, where everything breaks up into nice geometric shapes. Here you'd have a trapezoid, which you can even break into a rectangle and a triangle if you want. Here we got a quarter circle, which would be 1/4 pi r squared. Here we got another quarter circle. Here we got a triangle. We can find all those areas using just geometric formulas. Then their other option is just to approximate. Like maybe you just count squares. If we didn't know, like for example, if we had a parabola here and we wanted to do this area, the best we could do is count those squares. Because we don't know how to do the area. That's not a geometric shape. Okay, so those are our two options right now. Now by next Tuesday's quiz, we're going to be able to do better than this. We'll have figured out a way that we can do that. Okay, well maybe by next Tuesday's quiz, we'll see. All right. So, questions. So what you had is you had the first 14 or whatever, 2 through 14 or whatever was using this picture. Some of it was going backwards, so you had to do opposites and stuff like that. And then you had ones where you had to draw the picture. Okay? So like the one that was in the video. This one here. This is the V graph shifted one left. Right? So from 2 to 5, you should have been able to find that area. It's just a trapezoid. You can find this point right here, which was 3, and 5 plus 1, that would be 6. And so you should be able to find that area using either a trapezoid formula, that's probably the fastest, right? Your basis here, this would be 3, this would be 6. And then what's the height of our trapezoid? This is actually the height of the trapezoid. It's trapezoid tipped up on its end. And so that'd be 3. Right? And so you got whatever that comes out to be. 27 over 2, 13 and a half. Right? So that's just how you do that section there. Go ahead and graph them. If they make lines, anytime you got lines or parked circles, you're going to be able to do them. Yes?
25.
What was 25?
Use the fact that the definite integral from 0 to pi is u squared du equals pi third over.
Okay, now, what's the graph of y equals x squared look like? What's y equals t squared look like? What's y equals u squared look like? Y equals z squared. It doesn't matter, right? X, Y, Z, German shorthand, doesn't matter, right? And so this in here doesn't matter. If you want it, they could have written that the integral of x squared dx equals pi cubed over 3. All this means is you got the function y equals u squared or x squared or whatever, and if you want to do the area from 0 to pi, which we have no idea what that area is, because it's not a geometric shape, they told it to us. They said it's pi cubed over 3. So then what was the problem on 25 then, Connor?
The same definite integral from 0 to pi. And then in parentheses pi squared minus 3t squared. Of dt.
Now, I usually don't put those in parentheses, but you can, but it's fine. Just separate tells you that's the function. So what they're trying to get at here is having you use this stuff right here. Okay? These two rules. That's all they wanted you to do. So that means you take this and you write this as the integral 0 to pi of pi squared dt minus, and then the 3 we can kick out in front, t squared dt from 0 to pi. Now what did we just say that this red thing is right here?
That'd be negative pi.
Wouldn't be negative.
Well, it'd be minus pi.
Well, because of the minus here. But it'd be pi cubed. This is the red thing is what I was saying. The red thing is just pi cubed over 3, right? Now, and then of course when you multiply by the 3, right? Now what is this? Well, right. But this right here, here's the secret to this. What is pi squared? That's a number. It's just like having a 7 there. So that tells you your function is 7, or pi squared. What's the graph of y equals 7? Horizontal line. So anytime I have an integral of 4 dx, or I have an integral of negative 2 dx, all that is a horizontal line. At y equals 4, or at y equals negative 2, right? If I have an integral of just a constant, that's a constant function. It's just a horizontal line. So this would be, so pi squared would be a horizontal line at pi squared from, and then I'd want the area from 0 to pi. So what's that make? Makes a rectangle, right? Makes a rectangle. And so its width is pi, its height is pi squared. Pi times pi squared is pi cubed. That's why it's pi cubed. The 3's cancel. Pi cubed minus pi cubed is 0. Now, if I wanted to actually graph this in blue, if I wanted to take this function, I'm guessing it, well, I'm not guessing, it would be a parabola that's what? Stretched. What else? Upside down. Shifted up. Pi squared. So this would be a parabola that's stretched, shifted up pi squared, and so I'm guessing the pi must be over here somewhere. And so what do I have? I have some area here, and I have some area here, and those two areas must what? They must cancel each other out, and that's why I'm getting 0. So the idea is that if I took this and I actually graphed it, be an upside down parabola shifted up pi squared, I'd be looking for the area from 0 to pi. Some would be positive, some would be negative. Turns out that they would actually cancel each other out because we got an answer of 0. But that's only because they told us this part, because right now we don't know how to find this. We will figure out how to find it, but just not quite yet. Okay? Right now we can type it in the calculator, and that's true. This is, you can type that in your calculator. That wasn't the intent of any of this assignment. And the quiz next Tuesday is, I think, all no calculator. So don't be planning on that. Okay, what else? 38, right? Okay, 38. So 38 is kind of relates to the way the video opened up, where I had you look at these numbers and try to figure out how far the car had traveled. Okay, So if we take this as this is a velocity graph, okay? So this would be miles per hour right here. 60 minus 20t, so this would cross up here at 60. Oops, cross here at 60. It would go down with a slope of 3. It would cross here at 3, 2, 1, like so. That would be 60 minus 20t, okay? Or it'd have a slope of negative 20, I guess I should have said, okay? So it would look something like that. And it says evaluate the area from 0 to 4. In part A, well, this is easy. That's a triangle. That's 60 times 3 is 180 times a half. That's 90. So this area right here would be 90. What's this area? This would be down here at negative 20. So 20 by 1 and then times a half. So that'd be negative 10. So the area of those two together would be, so the integral from 0 to 4 of v would equal 80. That'd be 80 what? It said interpret that answer in car talk.
In car talk.
That's 80 miles east. It's displacement. It's where you ended up, 80 miles east. So the car actually went 90 miles east and then 10 miles back to the west. It ended up 80 miles east. That's displacement. Of course, we know that from velocity discussion we've already had with the chart. If this is velocity, it's like the derivative. When it's positive, the original position was to the right. So this is going, this is moving to the right until it stops, and then it's going back to the left. Okay? So all those things still play into it. Okay, B would be hard to do because I haven't given you that formula yet. So let's skip that here in a second. We'll come back to it. Let S be the speed. Now, what would be the speed? What do we say about speed? Speed is the absolute value of velocity. What's it do to this line? It flips it up. It becomes a V graph. Anything that's negative becomes positive. So all of a sudden, this area becomes positive 10, which would be, now the integral of the speed graph would be 100. What does that mean? Interpret that in car talk.
The average speed of the car
The total, not average, I mean, it would do with average or speed. The total distance traveled is 100. Wow, that's going to be nice. Remember what we were doing total distance traveled not that long ago? And we had to find when it turned around, right? We had to see where it started, where it ended, and then add all those up, right? That's how we did total distance travel. We just found a really cool way to do total distance travel right there. All we need to do is the integral of the speed graph. Do the absolute value of the velocity graph, do the integral, that'll just automatically give us total distance travel because it's gonna take care of all that turnaround stuff for us because the turnaround part is where it flipped up. So 100 is going to be the total distance traveled. So the integral of velocity is net distance traveled and the integral of the speed is going to be total distance traveled. Those are two facts we're going to use a lot here later on. Okay? All right. Well, and then D says, what's the average speed between 0 and 4? Well, I'm going to show, well, excuse me. So, well, you guys can tell me, what's the average speed? What's the average speed? 100 divided by 4, 25. He went 100 miles in 4 hours, 25 miles per hour. What's the average velocity? Part B. Isn't it just going to be this divided by 4? Now, average velocity doesn't tell you near as much information because what if you went and drove east for a long time and then drove west and came home? What was your average velocity for the whole trip? 0. Because you got positive velocity and negative velocity, and those are going to offset each other. And so your average velocity is actually your net distance traveled divided by how long you were going. Well, if you come back home, your net distance traveled is 0. So average velocity is usually not that great of a, or that useful of a figure. Average speed, on the other hand, would be more useful. Okay? But it's just those divided by 4. Okay? So it's this answer divided by that. That's a good lead into what I was gonna, there's two things we have to talk about, put in our notes right now. So that's a good lead into one of them. So let's do that one right now. Okay, this is called the average value of a function f of x. The average value of a function. Now, here I have a function, blue function f of x. Okay? Now, they call it the mean value theorem for integrals, but we're going to use the term average value. So the average value of this function. So doesn't it make sense that if you took all of these blue y values, that somewhere there's an average of those? Does that make sense, that there would be an average of those? Now, the junior high way of doing average is you add them all up and then divide, right? Well, how many are there? How many y values between A and B? So much for that theory, right? So much for that method. We're not going to be able to add up all the y values. But it makes sense that there is an average somewhere. Would you say it's about here? Higher, right? I'm talking the y values. From this y value right here up to this y value here. So this isn't high enough? Would you say it's about here? Higher? Oh, lower.
Keep going.
All right, some of you saying up, some are saying down. Leave it right here. Okay? So aren't you kind of figuring that you got some y values here? Some y values are above, you got some y values are below. You kind of want to offset those, kind of, right? Kind of middle, kind of what we're looking for. Okay? But since we're talking about area, here, this blue area would be this, right? Using our new notation, right? That would be this blue area, right? Would you give me that?
Yeah.
Now, what about this purple area? It's a rectangle. What do you think about the purple area compared to the blue area? Is it reasonable they be the same? Think what we were trying to do. We were trying to find a place where you had about as many y values below as above, right? Well, in doing that, what do you suppose happened with the areas? Doesn't it look like this area kind of offset this area?
Yeah.
This area might offset that area? Just that process of getting in between the y values seems to have kind of done the same thing for area. What would be my formula for this area? It'd be this width. What would be that width? No, it's not 8 plus b. If this is 2 and this is 6, it'd be 8.
Oh.
What is it?
B minus A.
There you go, b minus a. And then what would be this height? Well, isn't it whatever our average value is?
Yeah.
I mean, if this is our average value right here, that would be the height. So let's call that, we'll just call that average value. Right? So it'd be b minus a times our average value. So if I wanted to find my average value, couldn't I just take and divide over here by b minus a? So doesn't it seem like my average value would just be the blue area, if I could find it, right? Wouldn't it just be the blue area divided by the width? Because the blue area is the same as the red area, right? And I can't find the red area without knowing this value first, right? So that doesn't help me find this value. I can't find the red area unless I know this value. But I could find this blue area. Not yet. We haven't learned how yet. It's not a geometric shape. But if I could find this blue area and then divide by this width, wouldn't that give me this height right here? Yeah. My average value. And that is exactly our formula. And that is exactly what we just saw happen in this problem right here, where we did our area and then we divided by the width of the interval. So the average value of a function is, and we'll just write it, average value is equal to the integral of the function divided by b minus a. Now sometimes that's written this way. Sometimes you'll see that written this way. Either way is fine. I usually write it the top way, the top version. But this isn't bad either. So sometimes you see this. So I want you to think of it's average value of a function. Okay? Average value of a function. Comes from taking the area under the function divided by the width.
Good morning, and
Yeah.
pardon the interruption. This is just a friendly reminder to students. After you have finished your lunch and cleaned up your tray, table, and setting area, please return to your original seat and remain seated until the bell rings. Please do not stand beside your table or congregate anywhere in the cafeteria while you're waiting for the bell to ring. Thank you. Please remember to be responsible, be respectable, and be a Bearcat. Thank you.
All right. Listen up here now. Yes. Follow. And then when you walk, walk along the yellow line. Single file. All right.
Left foot, right foot.
Okay, listen. Now, okay, in your notes, you're going to want to write this too. So this is going to be something that be on today's homework. A lot of the homework will be very similar to what today's homework was, but this isn't really called anything. It's just a little formula here. So if you see what's written here while you're writing, I'll just talk about it. Kind of makes sense. The first one says the integral from A to B. So the integral from A to B, which would be that black area, right, that total area, is equal to the area from A to C, which would be the red area, right, plus the area from C to B, which would be the green area. So that kind of makes sense. The black area would equal the red area plus the green area. And you say, well, that's
Revolutionary.
yeah, wow, eye-opening. That's unbelievable. Well, now, but does it matter? So that's the reason that's so easy is because the C's in between the A and the B. Would it matter if they weren't? In other words, would the area from A to C, and I'm going to use kind of my shorter notation here, but would the area from A to C, and what I noticed here is how the C is in between, so I put it up here, right? Would it matter? So could I write, and one other thing I noticed here is that my integral goes from A to B. Well, it starts here at A, and it ended here at B, right? I noticed that in my two integrals. I split it up. So the question is, what about this? Then what if I went from A to B plus the integral from B to C? In other words, now I've got B kind of in this middle spot, and I've got, it starts at A, and it ends at C. Would that work?
Yeah.
Well, what's the area from A to C? That's the red,
Yeah.
right? What's the area from A to B? That's the black. What's the area from B to C?
Negative green.
Negative green, because it's backwards. So is the red equal to the black minus the green?
Yeah. Just do that.
It is. The red is equal to the black minus the green. So it seems really obvious when the C, or this number up here, is in between. But it doesn't have to be. So I could do another one. I mean, I could make these up all day probably. Well, there's probably a limited number you can do, but let's say the area from B to C. The area from B to C would equal the area from B to A plus,
A to C.
no, yeah, A to C, because remember, these have to be the same here and here. And then this has to be my start, my end. Well, what's the area from B to C? That's negative green. What's the area from B to A? That's negative black. What's the area from A to C?
Positive red.
Positive red. If you took negative black, added the red,
Negative green.
what's left would be the green, but it'd be negative because the black was bigger and it was negative, so it'd be negative green, and it works. So what that tells you is, if I was going to do the area from, say, 3 to 7 of some function, I could make that be, as long as I did 3 there and 7 there, what could I put here and here? 200. Any number. It doesn't even have to be between the 3 and the 7. Right? If I put 100 here, right? That would be the area from 3 to 100. Let's just say it was positive, and it actually works if some of that area was negative, but then it gets really confusing. But if we did this area from 3 to 100, and then we took the area from 100 to 7, which would be this, but negative. So you took the area from 3 to 100, which is all this, then you added the blue, which is negative. What are you left with? 3 to 7. So now you might be wondering why we didn't want to do that, and you're right, it doesn't come up that often, but it is going to come up from time to time. So what it basically says is we can take any area, we can split it up into 2 other areas that will be guaranteed to add up to that as long as we follow this pattern right here. So you're going to have some homework problems where you have to do that as well. Like that, you mean? Good point. All right, so the homework is 2-part. So if back to that assignment sheet, so it's basically what you didn't do in the book before, and then this right here, which is this packet. Now remember LH, that's Larson and Hostetler, stands for the authors of the book this came from. Let me show you in there what's going on. So your book problems kind of are these last 2 new things we talked about. It'll have some average value in there. Probably got some stuff where you're splitting up integrals into various parts. It'll also have probably some review stuff from what you did yesterday. This packet is more like what yesterday's work was. It doesn't take real long, but I do want to make one notation here, and that is that notice this, we're not starting in the front of this packet. It says LH page 289. This is 279. Okay? One packet short. Okay? Not very good with numbers, but I thought I could count before. All right. So 279. So go to the next page. 289, right, is the second page. That's the page we're doing. Now, you notice you're supposed to do 1 through 20, except omit 6 and 7. Now, 1 through 10, it just says set up the integral. You don't need to evaluate it. Well, I think you should. If it's just triangles or parts of circles and you can find the area, I think you should, because we normally would do that. We just set up and write the integral with your notation and everything. The ones that are parabolas, stuff like that, you can't find the area. And then on 11 through 20, you do like you were doing today on 15 through 20, whatever that section was, where you're going to graph them. So at 11 through 20, you should have pictures, and then you're going to have some triangles and some shapes where you can find those areas just like you had today. Okay? So, LH 289, and then those other problems in the book. Oh yeah, those packets. Yeah, if you've got them and you want to get them out of your notebook, yeah, that's fine. Let's get. I forgot to pick them up first block. I mean, I am definitely giving you a grade for them, so go ahead and we can pass them up.
Do you want them together?
Oh, okay. That's fine.
Do you want them together?
Let's do. Oh yeah, let's do. Yeah, just give me exam 2 first. Or if you already passed them up, then the person in the front row can separate them, I guess. Exam 2, Devin, you got yours.
Yeah, he thought, so I have 17.
Okay, so exam 2, yeah, we were supposed to Friday, and then I forgot to leave that direction for the sun. So, exam 2. Exam 2. Okay. Exam 2. Exam 2.
Today?
Yeah, we have a one.
Okay, exam 3.
This is so dumb.
Look,
I think it's funny because you said you can't assign it to a person or I thought it was Tuesday, Wednesday, Thursday, the meetings were local. How do you assign it?
Oh, I think we're going to this one Monday, all one, then you choose Tuesday.
So we have a meeting.
There's 5. We have one.
Oh, it's walking. I saw some crazy facts about how much Americans eat on Sunday night. Yeah, we sold like. But that's possibly. This is funny.